Okay, so we're going to continue on, and we've got just the very tail end here of our Module 1, Chapter 11 to get through. We've got a couple more problems to do, one kind of last section of concept to finish up so that you can kind of button up that homework that we have for Module 1. So the last subject here is looking at tangential and normal components of acceleration. This is nothing new. All of you have had kinematics, and I think everybody has had kinematics with me. So we did talk about acceleration, and we saw that acceleration when we are on a curve or on a curved path has two components that make up the total acceleration, and those two components are tangential and normal components of the acceleration. So, if we take a look at the next slide here, these equations look familiar to us, okay? So first of all, you're going to notice that we have the total acceleration squared is going to be equal to the normal component squared plus the tangential component squared. This is because this is a form of the Pythagorean's theorem. If you would, the acceleration squared is like our c squared, or that hypotenuse of a right triangle. And then the normal and tangential components of acceleration are going to be like the legs of a right triangle. So if we wanted to solve for the magnitude of an acceleration that is on a curved path, we can take those normal and tangential components to solve for it. Okay, so that looks familiar to us. Now, if we notice here the normal component is always that component that is going to go from the point, and it's going to always point down towards the center of rotation or the center of the curve. That's what, if you would, is pulling it into the curve. Okay, that's the acceleration. If you recall from physics, you are accelerating when you're speeding up or slowing down, right? But you're also accelerating even if you're going at a constant rate or a constant speed when you are around a corner, because there's that component, that normal component, that is pulling you into that curve. I like to say, you know you're accelerating when you can feel it. You can't feel constant velocity unless you're looking outside and maybe seeing things pass you. But if you had your eyes closed and you're in a car, for instance, and you're going at a constant velocity, it feels like you're standing still. But if you're slowing down or speeding up, you always feel that. Or if you're going around a curve, that means you're accelerating. Okay, let's just look at what each one of these components looks like when we are on, if you would, a curved path. So I'm going to go underneath my camera here, and I'm going to use our familiar example, kind of like from a kinematics point of view, where I'm going to use my frame member, okay? And I'm just going to draw a simple link, all right? So this would be my number 1. This would be my number 2. And this link is going to go around, and it's going to have angular velocity. So it's going to rotate around the fixed center that we see here. Now, the end point has a straight line velocity component, and that straight line velocity is going to be perpendicular to the radius of rotation. We're going to call that phi in this class. Otherwise, it would be a lowercase r, if you would. It's just the length of that link or a radius arm. And it is going to be perpendicular to that in the direction of angular velocity. Okay, we know that. Now, acceleration-wise, if we are speeding up or slowing down, these components of acceleration are going to go in the same direction. So our tangential, acceleration tangential, is going to go in the same direction as the motion or the velocity when we're accelerating. Okay, that means we're speeding up. Okay, notice that it's along that path. Okay, it's in line with that velocity or perpendicular to the radius of rotation. Okay, now if we're slowing down, I'm going to draw it as a dashed line just because it would be in the opposite direction. This could also be an option for tangential, but if it's opposite the direction of motion, this would be decelerating. Okay, decelerating. Now, Those are the tangential components. They will always be perpendicular to the radius of rotation. Okay, so perpendicular to that, and they're either going to go in the direction of motion or opposing it, depending if we're accelerating or decelerating. Easy, right? Now, direction of the normal. The normal is always going to go from the point that we're interested in, and it's going to point towards its center of rotation, which happens to be this way. So this is going to be our normal. That's always the case. This is that component of acceleration that pulls it into the curve. Okay, so when we're going around, this is the one that's keeping it in a curved path. Okay, so those are our components of acceleration. Now, I did add these to my equation sheet. Now, if you want to add these to your equation sheet, totally up to you. These are going to be the equations that we're going to be using in these last two examples and kind of finishing up this section. So what I have on here is that illustration that I just showed you. Okay, so just so that we know directions of these components of acceleration and how they relate to something that we've already kind of, studied in our previous class. You'll also notice that I have this Pythagorean theorem form of the total acceleration is equal to the square, what would be the square root of adding the normal squared plus the tangential squared. So here are the two components, 90 degrees to one another to get the total acceleration. Okay. Then lastly, what I have over here are the two equations to calculate the tangential and the normal component. So I'll kind of go in a little bit further. So first, the tangential component. We're going to take the change in velocity. This is if we're speeding up or slowing down. Okay, so it would be the final minus the initial divided by the amount of time it takes for us to make that change. Okay. Again, sounds familiar from kinematics. We use that. And then I just have the note here. It's going to be perpendicular to the radius in the direction of either acceleration or deceleration. And then the normal component is going to be calculated using the velocity squared divided by phi. When we were in kinematics, we used the lowercase r for this variable. In this book, they use phi. Okay, it's the radius of the curve of the curved path. Okay, so I'll give you a little bit of time if you want to either take a picture of this or if you wanted to jot it down. I'll bring it back a little bit later too. So if you don't get everything down, but I'll give you a little bit of time here to grab this because I'll be referencing it in the problems that we end up doing. Yeah. What do I have written at the top? Let's look. So this is top left, curvilinear motion, acceleration components. So this is when we're going around a curved path. Mm-hmm. Yeah. And this is really what's kind of on that slide, if you would. All right. Now, I also want to just let you know, remember, as part of your practice problems, you will be handing in an equation sheet. I've been kind of pulling mine in and out. If anybody wants to take a peek at mine and kind of see what it looks like, I can, pull that out. But I also want you to generate it. I used to share it with students or put it as part of, the lesson plans. But I don't know. I think it's kind of nice to make it your own. Okay. And so just something. I want to see that you have an equation sheet. You have something that you're referencing these concepts and equations because I don't expect anybody to hold them in their memory. Okay. So with that, I'm gonna go back to our slide. So this is really looking at that. So kind of looking at the normal here, normal component of acceleration, it will always act along the radius of rotation. It's going to point to that center of rotation, okay? The tangential is always going to be perpendicular to that radius, and it's going to be in the direction of acceleration. So again, if it's speeding up, it's going in the same direction as velocity. If it's slowing down, it's going to still be perpendicular to that radius, but it's going to be opposing the motion or the velocity, okay? All right. So let's look at our first sample and kind of put these things to work in, application, if you would. So we're going to be looking at sample problem 11.6. 11.6. I'm going to go underneath. I kind of like looking here more than at the problem there. I'm going to zoom in. Okay. So what we have here is we have a motorist is traveling on a curved section of the highway, something we're all, I think, familiar with and can relate to. The radius of that curve is 2,500 feet, and they're moving at 60 miles per hour. The motorist suddenly applies the brakes, causing the automobile to slow down to a constant rate, or slowing down at a constant rate. If the speed has been reduced to 45 miles per hour after 8 seconds, determine the acceleration of the automobile immediately after the brakes have been applied. Okay, so we are going around a curve. So now we are going to be considering those tangential and normal components to help us find the acceleration. Okay, so let's start the problem. So I'm gonna put this over to the side here. Okay, start at the top here. So this is going to be, this is kind of far up. Sample problem 11.16. And again, this is one of our practice problems. This is on page 697 in our book. Okay. And as we look here, the information that is given to us is right at the beginning of the problem. It tells us that that radius of the curve, which is going to be this Greek letter phi, is equal to 2,500 feet. Okay. We also know that the initial velocity, so the starting velocity of the car going around the curve is 60 miles per hour. Okay. And then the finish velocity is going to be 45 miles per hour because it's slowing down as it goes around that curve. Something we probably all have done, right? We go into a curve, it's like, oop, I'm going a little fast, put the brakes on, and we got to slow down a little bit here, okay? And the time to slow down from that 60 to 45 is going to be 8 seconds, okay? So that was given to us in our problem. They want us to find, okay, the acceleration. And this is the total acceleration, like the resultant acceleration. So I just have a little note here for myself. To find that, we are going to have to find the tangential and plus, I'm going to put it in the equation form, plus, so we have to find the tangential and the normal components of the acceleration. Okay, so just what we had just kind of reviewed and looked at on the slide previous. Okay. Now, as we get started here, units. I've been giving you a little bit of a break here. I've been telling you in dynamics, the problems get longer and longer. And honestly, I find myself not even wanting to put the units in. I mean, me. And I'm kind of a new units nut. But what I want you to do at the beginning of every problem is to make sure that all of your units are in the same form, okay? When we are in English units, as we are right now, we want all of our units in feet and seconds. So we need to convert the two velocities here to get into feet per second. Right now they're in miles per hour. So that's going to be the very first thing that we do. Look at your units and make sure that they're all consistent. If not, we're going to do some conversions. So the first thing is we want to do these conversions. And we want to make sure that we go from miles per hour to feet per second. Okay, feet per second. So for our 60 miles per hour, so 60 miles per hour, we are going to do 1 mile, 5,280 feet on the top. Miles is on the bottom, 5,280 feet on the top. So miles cancel. Make sure you do the cancellation. Sometimes I get people that are students that write this out and they never cancel out a unit. I'm like, no, no, no. Make sure you do that because you want to be sure that you have the right stuff left over. So we're in feet on top, which we want, but now we're in per hour. So we need to take that 1 hour and that goes on top, and we're going to have 3,600 seconds on the bottom. Hours cancel. So what I don't have canceled is feet per second. All right. So that means that my initial velocity should come out to be, and make sure you verify this, 88 feet per second. Okay, so this will be the value I use when I need to in equations coming up, not the 60 miles per hour. So go ahead and convert the final velocity, 45 miles per hour, in that same format. Okay, so you're going to use the exact same thing here and then calculate the final value. And you should get the 66 feet per second. Okay. Everybody gets 66 feet per second and 88 feet per second for the two velocities. Okay, awesome. All right, so now what we're going to do is we're going to look at the acceleration and how things, how things kind of come out based on the diagram. So all I'm going to do is just draw a diagram here representing that vehicle at that point along the curve. Okay, so my little dot here, this end point is going to be the vehicle. This is going to be the center of that curve. Okay, so the radius here, phi, okay, phi is going to be equal to that 2,500 feet. Okay. Now, as that car is moving along, okay, we know that its velocity, okay, is going to be perpendicular to that radius. And it is going down and to the left. Okay, so its initial velocity is 88 feet per second. Its final velocity along that curve is 66 feet per second. Okay, so depending on where we're at. Now, we're told in the problem that as it goes from 88 to 66, we put on the brakes, right? So that means that we are decelerating. So the direction of the tangential acceleration is going to oppose motion, okay? So this is going to be our tangential acceleration, and it represents a deceleration, right? Because we're going to go from 88 feet per second to 66. And again, it's perpendicular to that radius. So it's along the same line of the motion. It's just opposing it. Okay. Now the normal component of acceleration is going to go from the vehicle and it's going to point towards the center of rotation. So this is going to be the normal component. Now we can see that these two are 90 degrees to one another, right? I'm gonna actually put my AN on this side. So our final acceleration due to the tangential and the normal components, you can see is going to go and be the resultant of those two forces, right? And that's why we use the Pythagorean theorem form, all right? So we want to find this acceleration, but we're going to find or we're going to calculate those tangential and normal components to get there, okay? So we're going to calculate tangential and the normal to get started here. So I chose to go with the tangential first. So I'm going to say that the tangential acceleration is equal to, I'm going to go to my equation sheet. My equation sheet says that it is going to be the change in velocity, which is going to be the final minus the initial, divided by how much time it takes to get there. So that means that I'm going to have my VF minus VI. Divided by my change in time. My value for the final is going to be the 66 minus the 88, which is right up there, divided by the 8 seconds. Now notice I didn't put my units in because I already kind of made sure that they were all consistent with feet and seconds. So my tangential acceleration is going to be a negative 2.75 feet per second squared. Now, this is not a final answer. I'm going to put my little cloud around here. Final answers are going to be boxes, okay? So we're going to use that. Now I'm going to find my magnitude of my normal component of the acceleration. So the normal component of acceleration is going to be equal to velocity squared divided by the radius of the curve or the radius of rotation. So I'm going to go like this, velocity squared divided by phi. Now, which velocity? I've got two of them. So the problem says they want us to determine the acceleration of the vehicle immediately after the brakes have been applied. So that means that it's the initial velocity that we're going to use. So it's going to be the 88. Okay, so it's because it's right at that point when we start applying the brakes. So we're going to put the I here. Okay, so that means we're going to use 88. Don't forget to square it and divide by the 2,500 feet. So our normal component should come out to be 3.098 feet per second squared for the normal component. Okay. So now we have what we need to calculate the acceleration of the vehicle, or if you would, the deceleration of the vehicle. So A is equal to the square root of the tangential squared plus the normal component squared. So go ahead and plug your values in and calculate that total acceleration. Even though the negative is on the 2.75, because we square it, it becomes positive, right? So that doesn't really have a bearing on the value itself. Okay. Did you get 4.14 feet per second squared for your acceleration? Yeah. Yeah, there you go. So that's our first problem. Are there any questions on 1116? Kind of scooch in here just in case you need to grab any additional information. All right. So good. Okay. Then we have one more problem in this chapter that we're going to look at, and that is going to be 1117. So I'm gonna put my 16 aside. Okay. I can always pull it out during our break or a little bit later if you want to, or lab. No problem. And we're going to look at problem 1117. So 1117 says determine the minimum radius of curvature of the trajectory described by the projectile considered in sample 1110. We did 1110 last week, okay? So we'll look back at that. So if we go back to page 672 in our book. I'm going to pull out the problem first. This was the problem that we looked at. We had a trajectory that we were going off a cliff and we wanted to know, how far it was going to go and how high along that projectile. Okay. So what we want to do is we want to use this projectile. And here is, if you would, the example diagram that we created. So we're going to be interested in this projectile and we want to know right at the tippy top here. Okay, what the radius of rotation would be using the normal and the tangent, or I think it's just the normal. I have to look. I think it's just the normal we need. Okay. So we're going to use this information from here. And we also need to know that this velocity was the initial velocity in the x direction was 155. Okay, because that's going to be the component of the velocity going horizontally. So let's take a peek at how we're going to set this up. Okay, so this is sample 1117. Okay. And what we're going to do is I'm going to draw that projectile just so that we have kind of a frame of reference on where we're getting some things. Not the entire thing, but this was the start point. And I'm going to kind of draw the projectile going like this. Okay. The velocity original was going at a 30-degree angle. But then we had those components of the projectile motion, which were the initial velocity in the x direction and the initial or the original velocity in the y direction. Okay. Now we want to find the point at the very tippy top. We want to find what the radius of rotation is. So the easiest place to go is going to be at the top because our equation that we're going to be using is going to be the normal acceleration component is going to be equal to our velocity squared divided by that radius of rotation. And if we look here, that's what we want to find. We want to know what is that radius of rotation. Okay, so this is going to be our unknown. Well, at the very top here, this is moving along its path, right? So at the very top, there is no velocity going up, right? Because it's exhausted it. It's changing direction. It's going to start going down, but it still has that x horizontal component of the velocity. Okay. That's going to be the velocity that we put in this equation right here, because that's that point. That's going to be the velocity that it's using. And then it has an acceleration on it here, right? Now, what's the acceleration that's acting on that point going straight down? It is gravity, yes. So this is going to be equal to the acceleration of gravity. That's going to be our normal acceleration, okay? So our component, our x component, horizontal component of the velocity from problem 1110, so I'm going back to this problem, was the 155.88 meters per second, okay? So using this as our base, I'm going to kind of rewrite it. This is going to be our acceleration of gravity. This is going to be OX squared and that. So now rearranging this to solve for our radius of rotation. We're going to have our radius of rotation and we're just going to swap these two. So the velocity in the x direction stays on top, square it, and then we're going to divide by gravity. Since we are in metric units, our gravity is going to be equal to the 9.81. Okay, so now it's just kind of a plug and chug. So 155.88 squared divided by 9.81. What do you get for your radius of curvature? You get 2477 meters. Okay, very good. And that's it. That's that problem. Okay. So you have 3 problems left in module 1. This is going to be what you use for those last 3 problems. Okay. So you should be able to finish up now that module 1 homework. Okay. So are there any questions on sample 1117 at this time? No? Oh, go ahead.
The example in the homework, it's also for the radius that it's a very
Okay. Okay.
that same.
It would be using, okay, so the question, which problem is that? The last problem is which one? So there's a question on one of the homework problems. And what problem is it? Is it 145? 11.145? Yeah. Okay. All right. So for that one, yes. So you're asking, do you start here at that point where it starts? Yes, you will be looking at the acceleration. There's going to be a normal and a tangential component, and then you're going to be calculating them there too. Mhm. Because you need to find the radius at the initial where it starts, and then also at the top of the path. So there'll be 2 of them that you find for that problem. Okay. Yeah. And I think the final answers reflect that. Okay. All right. Any other questions? All right. Then that means that we're officially done with the concepts from module 1. So I am going to minimize this for a second. I'm going to go back to our assignment, which is the practice problems first. So now you would be ready to hand in all of the practice problems. I want to remind you, you do need an equation sheet that's listed here. So if you don't include an equation sheet when you hand in your practice problems, then you can't get the points. All right. So make sure that you do indeed do that. Some sort of a developed equation sheet that you have. Just as a reminder, make sure everything is neat and readable. Double check your files before you upload them, because sometimes I get fuzzy ones and then I can't read them and I can't give you credit. So make sure that you take care of that stuff, that they're good files when you submit. Okay. And then let's take a peek at the application problems. You're going to notice here that I have the application problems listed along with their final answers. And then if there's anything that you need to be aware of, the first two problems here utilize, I have you guys using the Excel spreadsheets. Okay, so it kind of feels like a long time ago. It was a week ago when we had covered that information. So kind of take a peek at these notes, make sure that you're handing those in appropriately. And then you're going to notice you have the final answers for the rest of the problems as well. Okay. Same thing with handing in. Make sure they're nice and neat, easy to follow. Make sure that I can see the files when you're handing them in and such. Okay. All right. Then if there aren't any questions, then I am going to stop recording at this time.